thanks for coming back. So title for today is geometric time theory. Well, I'm not sure it's really a good title, but my talk won't be literally about geometric time theory, but we will see. We'll see it play a role in what I will discuss today. So first of all, maybe so Max has explained to us this week how to construct like some refinements of the analytic prismatization with QP coefficients, like this filter prismatization and the syntomification. And then he also told us on Wednesday how to somehow extend this whole story to integral coefficients. What I want to do today is somehow to go back to basically the end of my third lecture. So I will only be concerned with the analytic prismatization and only discuss what happens for QP coefficients, right? Just to clarify, so I won't use anything of what Max has explained in his talk. But I will discuss the result that he has used several times. Okay, so the main result that I want to discuss today is the following theorem, which I think I already, at least informally stated several times. So I will let X be a smooth, partially proper rigid space over QP. And so let me recall maybe first that, okay, so I have defined this p-adic crystal stack. So I recall that this is basically just the Frobenius perfection of the analytic prismatization of X. And then I model Frobenius. So that's what I call the p-adic crystal stack of X. And I explained in my, I think, second lecture that this always receives a map from the Farg-Fontaine curve relative to X incarnated as a Gelfand stack. And this morphism is denoted alpha X. And so the claim of the theorem is that this morphism alpha X is prim, which is like a weak form of being cohomologically proper. And more importantly, alpha X upper star is fully faithful and it induces an equivalence between perfect complexes. From the category of perfect complexes on X equals 1, and the category of perfect complexes on this relative Farg-Fontaine curve.
If the statement is under some larger.
It's fully faithful on the whole derived category of, like a whole derived category of quasi-coherent shifts, solid quasi-coherent shifts in these stacks. But it's not essentially subjective, but it becomes an equivalence when you restrict it to perfect complexes.
Just ask a question about alpha again.
Right.
Correct. Alpha induces an isomorphism on the de Rham stack?
Yeah, that's also correct. So this there was also this morphism which I call beta X to the de Rham stack of div1, but this also coincides with the de Rham stack of the whole.
So just as a reality check, I guess this then means that the quasi-coherent complexes are not the end of the perfect complexes, since
yeah, it's not end of the perfect.
And is it like, is that true on both sides, or is one side like more finitistic than the other? Like,
no, it's false on both sides.
Yeah.
like if you do this in completion, I guess you only see like discrete modules, right? And here you really work with this category of solid.
So this perfect guy is a kind of perfect has a kind of discreteness.
Right. Yeah. Well, relatively discrete, so to say, because locally, in the affine case, like the ring has a non-trivial topology, but it's relatively discrete.
Yes, yeah, so, I mean, sorry to belabor that point, but just to kind of get some models. So can I think that, like, in a more classical situation, I might have some kind of reasonable topological ring, and then maybe finally presented modules over it might have a canonical topology. It's like the unique one that's kind of compatible with being an A module and so on.
Mm-hmm.
And so these perfect complexes are like more or less like that, like sort of something like that. But then the more general quasi-coherent solid guys could have like some other topologies that are not not so manifestly just induced by their A module structure. Like it's really an extra. So for these perfect guys, in some sense, the topology is just forced on them by the A module structure. But for the general quasi-coherent guys, the topology is really like extra data that they know and have chosen in some way.
Yeah, like this category on a ring, like the category of like perfect modules is really just the category of like usual perfect modules on the underlying ring. So it does not like. Yeah. There was another question? No.
I think I wanted to ask exactly about what you just said. So.
Good. And you can also characterize, we work in Gelfand stack, this is also the same as being generalized. Okay, so before commenting on this statement, let me finish, like add one more, like two more. I want to say that in fact, this similar result also holds on the hot state locus. In fact, whenever you have some open substack of the underlying arc stack, another statement which is true is that whenever you have U which is open inside like the arc stack underlying this relative arc content curve, you can just take via this morphism beta x, you can just look at the pullback of U, and you still have like this equivalence would still restrict to an equivalence over U. So you have a stronger statement, but let me just content myself with this and the observation that also the same happens on the Hodge-Tate locus, and let me write what it gives in this case. I will still write alpha x equals star, so then it's an equivalence between perfect complexes on the Hodge-Tate stack and perfect complexes on the fiber of this relative arc content curve over the Hodge-Tate locus, which is what I denoted previously by x diamond hat. And plus a relative variance of all these statements when x is not a smooth rigid space over QP, but again smooth partially proper over a perfect weight base. But then you have to do everything. So if this perfect weight base is called S, then you have to do everything relative, like all this construction will be relative to the far content curve of S. I explained before that one can construct relative version of this prismatization, and that's what one would need to use at this step. Okay. Right. So how should you think about this statement? So maybe as a remark, we should think of the theorem at least morally as a p-adic non-abelian Hodge series statement. This time I have some. Why is that? Well, here, if you look at the right-hand side, that's some kind of one way to describe what this. Let me restrict myself to vector bundles. This equivalences restrict to equivalences between categories of vector bundles, and that's something like relative, what you could call relative phi gamma modules over X. For example, if X is spark QP, that would literally be a vector bundle on the stack would literally be a phi gamma module over the Roba ring. And for X smooth rigid, you can imagine that this is just a variant where you replace the usual Roba ring by some kind of relative version, relative to X. So in particular, this is a category which contains always the category of Po et al. QP local systems on X, corresponding to slope zero objects. Right, so this is something like some generalized version of the category of QP local systems on X. And how should you think about the the left-hand side here, again on vector bundles? Well, there it's useful to remember the discussion we had last time about the geometry of this morphism beta X. Generically, it was on isomorphism, but it's not on the Hodge-Tate locus, and on the Hodge-Tate locus, XD1 is some kind of twisted version of the Hodge stack. So it's like it's a non-trivial gerb for the overconvergent Tate twisted tangent bundle. So the category of vector bundles on this stack is some kind of twisted version of the category of Higgs bundles, or maybe Higgs-Sen bundle in the arithmetic situation. But away from the Hodge-Tate locus, beta X is an isomorphism, so you just see the rank stack, so you have something like a D module on the relative far content curve. So a vector bundle on XD1, you can think of it as some kind of D module on the far content curve which degenerate to Higgs bundle. So it's sorry, a flat connection which degenerate to Higgs bundle. So very analogous. That's kind of justification for this name that we are considering the p-adic twistor stack of X. So something like a p-adic twistor. Okay, and so to repeat, what do we see there? I already implicitly said it. Again, on vector bundle, this would be like something like a Higgs bundle on X. And this is by definition, this is just a Po et al. Vector bundle. So this restriction of this equivalence to the Hodge-Tate locus is this kind of like some kind of p-adic Simpson correspondence result. Except that, of course, you could argue that the heart of p-adic Simpson is really about providing some condition under which, maybe under some additional non-canonical choices, this literally becomes a true statement that vector bundles, Po et al. Vector bundles are the same as Higgs bundles. So in other words, you can really identify this category of twisted Higgs bundles with Higgs bundles. And that's not something I have anything to say about. But yeah.
But do you know, like, if you start putting in those conditions, does it convert into a more classical statement, or you're not?
So what I can say here is that there is some kind of Cartier-Joule perspective on this result due to Bhatt and Drinfeld. So instead of using the Hodge-Tate stack, as I do here, they use something called the Simpson gerb. So I think they work maybe in this relative situation. So let's say, for example, when X is living over CP. And they prove such a statement. But I think they also... so Bhatt has some course notes on his webpage. They also revisit this result of Falkins and Ben Hoyer that if you assume that X is smooth and proper, then you do get, under some additional choices, you can really get an equivalence between Po et al. Bundles and Higgs bundles. And they have a way to interpret this in terms of the Simpson gerb. But I don't.
But they do somehow split the gerb or something.
Not quite. At least the Hodge-Tate stack will it's not that in the smooth proper case this will split. That's not the case. But still at the level of like vector bundles. So I think for the Simpson gerbe they cannot like literally split the gerbe, but maybe they can split it some more. Okay, I don't know.
Yeah.
So maybe I don't say.
Okay. But so probably some parallel statement is true here.
I would guess so. I would imagine that whatever they do, you can try to reinterpret in this. So there is a precise sense in which this is literally cartesial to the Simpson gerbe that has been worked out by Rodriguez Camargo. Okay, but that's maybe just some kind of heuristic of how to think about this result. I should also add that what this statement should admit conversion for the integral prismatization. So X is still a smooth rigid space over QP, but the prismatization is this integral prismatization that Max discussed on Wednesday. And here, as he explained, you have to replace this by just ZP local system on X. I think the proof that I'm going to discuss today should go through also in this mixed characteristic situation, but this has to be checked carefully. Sorry. All right. So how do we prove such a result? So maybe the first observation is that we have this morphism alpha x, so the statement is local on X for the étale topology. But my X was assumed to be a smooth rigid space. So locally, for the étale topology, X looks like Gm to the D, where D is the dimension. Possibly D can be 0 as well. And I provided in my third lecture, I explained a description of the prismatization, the Twister stack of this. Well, I did it when D is 1, but this construction X goes to XD1 commutes with finite limits. So you also deduce a description for finite products of copies of GM. So let me recall. So for the p-adic Twister stack, it was. So maybe let me, as usual, let me know to make my notation a bit shorter. Let me just now write X for Gm to the D, and X tilde will be this inverse limit perfection. Ingelfand stack, so an uncompleted perfection. And the statement was that it was given by X tilde relative to the cyclotomic delta space, which is we call it X sic. Is just this inverse limit. Q goes to Q to the P of 1 plus the disk. Minus 1. And then you mod out by gamma D LA, where gamma D LA, gamma D is just a short notation for ZP cross times ZP to the D acting by multiplication. I never know how to write some direct products, so you can correct if that's the wrong direction. Yeah, so at least I explained this statement when D is 0 and when D is 1.
So can you just remind me again what the subscript, like X6 as a subscript means?
I just mean based on, sorry. So it's a relative D-dimensional perfect analytic multiplicative group over this space. And, right, so now the main observation to be made at this step is that one can rewrite this. Like if one knows some sense theory, one can rewrite this in terms of locally analytic vectors. So already here in the denominator, I see this locally analytic p-adic group appearing, but this I can in fact. Wait. I think I may have. Okay, that's everything not Frobenius, I guess. And this I can rewrite as I take the far content curve for this X tilde over strictly cyclotomic, and this I see as diamond. And now I take this. So now this is a perfectoid space. Like this is a d-dimensional perfectoid rigid multiplicative group over this perfectoid extension of Qp. And I have a gamma d action on this, which induces a gamma d action on this relative far-content curve. So that's a true Berkovich space. And now let me write gamma d LA. And now I get a model. So I tell you, can rewrite this in this way, but so here there is a priori maybe some ambiguity about what I mean by this notation. And I will later introduce this notation in a more general context and give it a precise meaning. For now, let's just take it in the following sense that we have something which is, okay, this far-content curve is not an affinoid Berkovich space, it's like, it's time, but it's a union of affinoid pieces. And for each affinoid piece, I just look at the locally analytic vectors for this gamma d action on them. And a priori, there is also the question of whether I want to take the derived or underived. But the point is that precisely it will turn out not to matter because the derived locally analytic vectors in this case are concentrated in degree 0. And moreover, they are explicitly given by whatever I wrote before over there. So for example, when d is 0, this is a computation, so it's related to work of Rosenstein and Porat, which computes locally analytic vectors. So now the group acting is just ZP cross. So if you look at the far-content curve of the cyclotomic extension, and you compute ZP cross LA locally analytic vectors, well, the claim is that it is precisely given by this thing, which in terms of rings means that if you take the perfect Prober ring, or this ring of functions on the far-content curve, and you take these locally analytic vectors, you get basically just a kind of union of Frobenius inverse of the usual Prober ring. That's another way to put it. All right, so that's one way to rewrite this. And why do I want to?
So I guess this thing, is it 5 from 10 there, or is it the y?
Well, I somehow moved the Frobenius quotient inside because it's the one that was by definition the quotient by Frobenius of the perfect prismatization. Ah, you mean here?
Yeah, just here, like the.
Yeah, you're right. Sorry. Yeah, it will be like so. Yeah, correct. Right. So now I have this morphism alpha x from, let me write it, from far-content x diamond. But no, this is also known just by the usual perfectoid theory, or rather by the way this construction of Gelfand stacks of relative far-content curves in Gelfand stacks is made by Arthur-César. This is the same as this modulo gamma d continuous. So the continuous incarnation. Okay, so by localizing for the Étale topology, we reduce ourselves to proving the statement for x being of this specific form, and now we see that the morphism alpha x is very concretely given by passing from like the continuous quotient of the perfectoid far-content curve to its locally analytic to some locally analytic version, and so the strategy to prove the theorem would be to more generally try to understand, compare more generally quasi-coherent sheaves perfect complexes. On y mod g continues, and y mod g LA, so YLA mod GLA, when G is a p-adic group, acting on the Berkovich space Y. And here again, I have to specify what I mean by YLA, but it's of course with respect to the G action. And there will be basically two steps. There will be some general, first step will be some general results about decompletion by like derived locally analytic vectors. And the second step is proving that in the situations we care about, like, there is vanishing of this higher local analytic vector. And okay, of course, I won't discuss all these steps in detail, but I want to give an idea about how one is working. And for two, I don't think we have really anything really new to say about that. It's just that in some situation, like typically this example that we care about, one can prove that derived local analytic vectors agree with underived local analytic vectors by using standard techniques in sense or geometric sense theory, namely these states and axioms. I'm just checking that one can apply them in these examples of interest. So the second step will be just kind of a rather standard argument. What's maybe more surprising, at least to me, that there is a very general version of one which works. So I think the output is maybe that if you work derived, this locally analytic decompletion works in extreme generality. And then it's just that in concrete situations like this one, you can really, like, you have also vanishing of these higher local analytic vectors. Okay, so let me discuss a bit this decompletion. Okay, so in this part, so this is really about step one. So maybe just to recall, so everything will be done in this derived and solid setting. So G would be a given p-adic group. Then we have this category which maybe I denote by rep QP solid of G, which is just this category of modules over this. It was our algebra of G inside the category of solid QP modules. So that's my category of like, continuous representation of G. And there is this notion of locally derived local analytic vectors. So if M belongs to this category of solid representations, one denotes by MLA the derived local analytic vectors, which are defined by taking, so you take the group cohomology of G acting on locally analytic functions on G transfer with M. Right, so I think that's a definition, a description of local analytic vectors that appeared in Luere's class 2 weeks ago. I don't write it always, but of course everything is implicitly assumed to be derived, and the transfer product are solid transfer products and so and M is said to be a locally analytic representation. So you have a natural map from locally analytic vectors to M, and if this map is an isomorphism. Okay, so that defines a full subcategory, which I think I want to denote with LA, QP of G, inside this category of solid representation. So another way to think about this category of representations, you can also think of this as the category of sheaves on the classifying stack over spec 2p, G spec 2p of GLA. Right, if you want to think in terms of sheaves on classifying stacks, that's another way to think about this. The subtlety is that it's not true. This is not something that you can describe as sheaves on the classifying stack. So that's one aspect in which local analytic representations are better. But okay, so that's not the same, but it's something you can imagine as sheaves on the continuous incarnation. Okay, so I just write this symbol with no precise meaning to say that this is maybe something like what's true is that you have a functor from here to here, which I don't know if it's fully faithful. I think it is at least on nuclear objects. But you don't lose so much if you just replace this. I think all the examples we care about will come from this category, so that's better. And in this term, you do have a natural, so I just write point for G spec QP. You have a natural map from G continuous to GLA, just coming at the level of rings from the map from local analytic functions to continuous ones. And if I denote by H, it's morphism. Like this functor M goes to MLA. When you think to it in terms of classifying stack, it's really just a push forward. Right? So it's just given by F lower stack.
Yeah, so this is, I guess, a derived.
Everything, yeah, sorry, I should stress it. Everything is implicitly assumed to be derived in this discussion. Right, and this morphism F is proper. So in particular, you have a projection formula for local analytic vectors, and this formally implies that if R is an algebra object, a commutative algebra object in this category of solid representations, then RLA is also an algebra object. Okay. Right, so note that I have introduced these notations. I can state the theorem, which is like the precise statement we prove about point 1 in this agenda. So Y will be any Berkovich space with an action of G continuous. And okay, so then what I can do is I can consider the following map Y. So it goes from, I can form the quotient of Y by this G action. And this is something I maybe did not stress enough in my first lecture. This, when you have a Berkovich space, you say realize as a Gelfand stack, you have a natural map from Y to, you take the underlying topological space of Y, such as the underlying Berkovich spectrum, and you take the corresponding Betti stack. So that's a morphism that you always have from any Berkovich space to the Betti stack of its underlying Berkovich spectrum. And notice G action on Y induces an action on the Betti stack of y, and this action will be will factor through G smooth. But I want to model by GLA. So here, this action is induced by the natural map from GLA to G smooth, so the smooth incarnation of G, plus action of G smooth on the Betti stack. So the Betti stack of Y is the same as the Betti stack of its Durham stack, and the Durham stack of G is G smooth. So this action is the action of G on Y induces an action of G smooth on the Betti stack. And I want to denote by just notation OYLA. So this will be the push forward of the structure shift along page. Sorry. Yeah. Okay, so now what I claim is the following. So H is proper, and H of R star is a fully faithful functor from the category of modules over this object, OYLA, inside the category of sheaves on the Betti stack. Mapping to sheets on
Does proper mean homologically proper, or does it have it more geometric?
It really means well, for what I'm going to say, I think it only matters that it is homologically.
But there is another meaning.
There is another meaning, and it can also be true. Okay, so that's my first point. So now this category on the source is a bit abstract, but the second part of the result is that if Y is affine, or affinoid, to say, for some Gelfand ring R, and maybe also G compact. I'm not sure this is really needed, but yeah. Okay, let me write it. Then this category we have on the source is just an explicit category. So it's just a category of modules over RLA, as like previously defined. So that's an algebra object in the category of locally analytic representations of G. Which is just another notation for what I denoted by FLA QPG. Then this is naturally equivalent to the category I have written on the modules over OYLA inside Okay, so concretely, this is saying that okay, when Y is assumed to be affine, so that would be here on the right. I have like spec R modulo G continuous, and here I have a category which, well, the point is that RLA is a priori derived object, so it's not an animated ring. But if you furthermore assume that RLA is in degree 0, is it my? No.
You could. I don't think so, but you could try turning it off. Try turning off the microphone. It's outside.
I don't think it's.
Okay. Then this is the same as just I can rewrite the left hand side is just sheaves on spec RLA over GLA. So you see that this is telling me that the statement I'm getting here is close to the kind of statements I care about.
Lost somewhere. I think you said this, but what is this absolute value of y Betty, and how does that correspond to RLA? Sorry, yeah, can you? Sorry, you said this absolute value of y Betty.
That's just underlying topological space. Yes. I take the Betty stack. So the claim I'm making in part 2 is that this category is the source of this function.
Oh, sorry.
So that's I stack. I claim that this you can explicitly, in the affine case, you can really just rewrite as modules over RLA, over the ring of local-analytic functions, in the category of local-analytic G representations. So this is a statement. You see the quotient by GLAs on both sides. So by descent, this will reduce to the claim that modules over RLA in the category just of solid QP modules is the same as modules over, or maybe some pullback of OYLA over the Betty. So I don't know. Here this is not like really means the pullback of what I like OYLA to the Betty stack. So that's some kind of, if you want, you have to think of this claim as some kind of quasi-coherent of OYLA. Like I have a topological space, I have some ring shift on this, and I'm claiming that modules over this ring shift are just given by modules over the global section. Because if you unravel, so how would you describe this, this OYLA? I recall, so I start from, so in this affine situation, I have G spec R, mod G, go to G spec R. Betty mod GLA, but if I just try to describe the underlying object, just the thing I get on the Betty stack, maybe just even in global sections, you see that basically you have to compute something like, okay, let even, maybe even say that I just care about what happens on global sections. If I have this going to point mod GLA, and then I pull back to the point, right? What I'm doing here is I'm pushing forward and pulling back. So when I look at this, it gives me something like GLA mod G. And you see that by proper base change, so assuming this map is proper as claimed, pushing and pulling back is the same as pulling here and pushing. But when you write down what you are doing, you have some G representation. Pulling back here is transferring by this ring of local analytic functions on G and then pushing. So it's just the formula I wrote down for taking local analytic vectors. Right. So this is saying that the global sections of OYLA on this Betty stack are really just given by RLA. And so I'm claiming that modules over this ring shift are just the same as modules over the global sections in the affine case.
Sorry, just to clarify, so for the reason that you said before, this modules on Y mod G continuous is not quite the same thing as I mean, you don't get these like you don't get modules over the group ring showing up at any point in these constructions. Is that right?
You don't get modules over.
Sorry, so you're taking quotients by G continuous here at all times. You're not taking like modules over. Sorry, so the thing on the board, the first line of the bottom board, that does not show up in.
Sorry, that was my definition of OYLA was defined to be this push forward. So if Y was just,
I think like you're saying that if you look at the first line on the bottom board, so go down, go there.
Sorry.
Rep QP solid G
yes,
equals mod QP solid of DQP. That first line, I think Akhil was asking if that connects to anything that came since.
Sorry, so that's been a little bit confusing because you explained that this is not quasi-co of an analytic stack, but you don't consider this.
Yeah. Okay. Sorry. I should have made, I'm really rather working with this, but maybe the more classical or classical. I think this has been developed by this derived on solid setting by Rodriguez Jacinto and Rodriguez Camargo, and I think they really work with this category to start with. I think in this situation it's more natural to work with this category. But they are not exactly the same. This is like co-modules over some a ring of continuous functions. But this is like really modules over some whatever algebra.
For example, they prove in that paper this fully faithfulness result, right? That locally analytic representations of G are a subcategory of all representations of G.
Yes, I think that would be fine with both versions. But you're right. Maybe let's take this as our category of continuous G representation and define the functor of local analytic vectors to be this push forward.
And for sort of classical objects, like coming from Bhatt representations and so forth?
Yeah, I think whenever the underlying solid module is nuclear, well, at least I think you have a fully faithful functor from this one to this one. Maybe it's even an equivalent. So where am I? Yeah, and finally, last game is that this pullback H upper star induces an equivalence on generalizable objects.
Maybe it would be better without the mic, sorry, but maybe it would be better.
Yeah. So,
I'm sorry.
okay. So you see that it's really parallel to the formulation of my first theorem. I wonder how much I want to say about the proof. So part one is really part one is not difficult. What requires most work is this part two. Maybe I can just try to say a little bit about the proof of this. So as I said, you have to prove some kind of quasi-coherence for this ring object on the Petit stack. And what you end up having to prove is that if you have a rational localization, then have to reduce to prove that when you take locally analytic vectors inside R prime, so this is the module of our local analytic vectors in R, and then you base change to R, and this is isomorphic to R prime. So that's some of the key statements you have to prove. So that's basically saying that you can find a locally analytic decompletion of any rational localization. Because once you have that, you can deduce that R prime LA is in fact an idempotent algebra over RLA. And then somehow you have a basis of closed subsets for your topological space, absolute value of Y. And yeah, somehow once you have argue with that, once you are able to prove that, then it's not too difficult to deduce a state. So maybe I don't want to really explain how one does that. And so how does one prove such a thing? Well, basically you reduce, by some devisage, you reduce to consider two kinds of rational localizations. And so you reduce to considering the case where R prime is something of this form, or R prime is something like this, with F is topologically important. Right. And moreover, so your rings are Gelfand. So you know that. When you reduce modulo sum, so the action of G on R is continuous. So you know that when you reduce modulo some big power of P, the action on F, maybe up to passing to an open subgroup, will become trivial. So in the end, you just have to show that you have a representation. So by taking M to be R, one of these, and taking maybe passing to any of these two, R prime, maybe it takes the power bounded part for R prime as 4. Then you see that there exists some S big enough, so that maybe up to shrinking G, you know that this representation M, so that has an action of G, and it will satisfy something of the following, something like this. When I look at this, tensor field with R less than 1 modulo P to the S, tensor with R. Then this is isomorphic to M modulo P to the S for some S, which is basically saying that this modulo P to the S, this representation of G will be as trivial as you can. And then the claim is that this implies that this locally analytic decompletion holds. So this implies that after you invert P and take these locally analytic vectors, so the more general claim is that whenever you have a continuous representation of G on some R less than 1 module, which satisfy such a property, then it's after you invert P, it has a locally analytic decompletion. So that's the idea here. Implicit idea is that some kind of assumption that you have. So for this, okay, I'm really oversimplifying. It's really important for this kind of implication to assume that the ring over which everything lives is p-adically complete. But R is a priori only Gelfand, so you have to do some further reduction to this situation. But here, so basically the claim is that when you have a G representation on solid modules over some p-complete ring, which is trivial mod P, some power of P, then it is locally analytic. That's the implicit claim, and this idea, the idea that triviality mod P implies local analyticity is an idea that always appears. I would say it's a rather standard idea in geometric sense. Like, to give a simple example, if G is ZP, with generator given by gamma 0, and you have a V which is a p-adic Banach space. And you assume that so that gamma 0 of V V0 of the unit ball is contained, so that the action is trivial modulo. I think it's okay. Here I'm not exactly sure of what the correct assumption should be.
Yeah, zero.
Gamma 0 minus 1, I guess, minus identity. Then you can show that the action is even analytic in this case, just by showing that for any V in V, then the following is in ZP, then the following expression this is somehow defining your action. And that this satisfies. So this is the same as the action of X on the vector. So let me just, before making the break, add one more observation. So that's basically maybe all I want to say about the proof of this theorem, and just to comment briefly about step 2 of this strategy. So you can make the following definition to really. So a priori, this gives us just some. If I look at part 3 here. So what does that tell me? That tells me that in this category of modules over OYLA, inside sheaves on the Betty stack, mod GLA, and then I will look at dualizable objects in this category. This is the same as dualizable objects on this sheaves on this Gelfand stack, but because this one is a Gelfand stack, this is just perfect complex. So that's the kind of statement you want to get for my main theorem, but when step 2 is needed to rewrite the left-hand side as really some category of perfect complexes on some Gelfand stack. And well, so again, let Y be Berkovich with a G action. And then you say that, okay, first if Y is assumed to be first affine, you say that Y is classically decompleted. If, well, maybe two things. RLA is connective, so it has nothing in higher degrees. So then it's automatically Gelfand. So then you have a honest Gelfand ring. And also, that seems like it would be good enough, but you also want that, this natural map from RLA to R, it's an isomorphism on uniform completion. And then in general, if Y is not necessarily affine, in general, you say that Y is classically decompleted. If you can find a strict closed cover, so a cover by closed subspaces, which is strict in the sense that each of them contains some open by affinoid. So the following form, Y is and this will be stabilized by not necessarily by G, but by some compact open subgroup of G, which I call GI. And you say that Y is classically decompleted if each of them is each of these Ri is classically decompleted for GI. And then you denote by YLA the union of this spec R. So some of this condition, second condition I put there is to ensure that some of the condition is independent of choice of covers that I pick, and that this glues well, so that this is something well defined. And if you are in this situation, in fact you can reinterpret this category of modules over OYLA. It's really just the same thing as, so YLA is now a Berkovich space, and I take YLA over GLA. And so you see that combining, under this assumption, you can rewrite this locally analytic decompletion result in terms of an equivalence of a fully faithful functor on quasi-coherent shifts between Gelfand stacks, which induces an equivalence on perfect complexes. And then to finish the proof of this main theorem that I stated at the beginning, you just need to check that in these examples of relative Fark-Fontaine curves over rigid analytic multiplicative group perfected, then indeed you have vanishing of higher locality vectors. And it's kind of computation for which you have to use the standard tools of geometric or sense theory or geometric sense theory. Okay, so after the break, I want to explain some consequences of this theorem. Okay, so let me continue. So I want to explain some consequences of both of the theorem, but also of this. Of these two. Like maybe first of this theorem about locally analytic decompletion. So here is one corollary of it. So the statement is a bit long. I will use. Sorry, it's a corollary of this. Of my main theorem at the beginning. So X is smooth. Okay, first. Rigid space over QP again, but you can also do a variant over the perfectoid base. And then I claim the following. So first, that maps from over G spec QP from X hot state to the classifying stack of GLA. So the claim is that this is the same as maps from X still over spec P of X diamond hat to PGLA. Sorry, so say G is any p-adic. Okay, so GLA torsors over X hot state, and this kind of uniform completion of X are the same thing. But this I can also rewrite as maps over the arc stack of QP between X diamond and B stands for, I don't know, for classifying stack you can either write them as point something, or I just write PG from now on. It's easier. G underline tors. So G underline, I recall, is just the arc stack associated to this topological group G. And this is so G torsor on the diagonal. So these maps are equivalences. So here this is just really like pullback along the natural map from X hat to X hot state. And here this is just induced by perfect realization.
Sorry, what's the subscript for the mass part for the maps on?
That's my notation for the arc stack of QP.
Oh, okay.
Something which maybe more classically, if you use the formalism of V stacks, you write spatty QP. There is a similar statement at the level of the whole twistor stack, but it's a bit weaker. So I claim that like GLA tensors on the twistor stack. So this is called induced by alpha x. This would be perfect utilization factor. So again, this alpha x upper star induces an equivalence between GLA tensors on x div 1 and the relative factor. But no, I can't quite rewrite, so it's again a spec QP. But here I can't really rewrite this as a statement just purely in terms of diamonds. But I can, however, do the following. So there is a natural morphism of anima between like maps over the arc stack of FP of X diamond to BG. To BG underline towards maps from 5 content of X diamond BG. Such that after perfect utilization, so what I'm doing here, so if I compose this with perfect utilization, I'm just getting, this is just induced, is sending a morphism from X to BG underline to you have 5 content of X diamond. That's described by the simple fiber product formula from X diamond times MRQT mod for layers on X. I'm like projecting to X. Sorry, I'm not saying this very clearly. Okay, maybe let me just say in words. If I have a G tensor, a G underlying tensor over X diamond, then I can just form the relative Fark Fontaine construction over there. And this will give me this gives me a G underlying tensor over the relative Fark Fontaine curve for X. Okay, so how should you think about this result? So maybe point 1 is just informally saying that G underlying tensors on the diamond like uniquely decomplete to GLA tensors on the Rochdale stack. And point 2 together with point 3, it tells you that if you have G tensors on the diamond, they give rise. So by point 3, they give me a GLA tensor on the relative Fark Fontaine curve, but then by using 2, I see that they give rise to GLA tensors on the twistor stack. So that's some kind of locally analytic decompletion for tensors under p-adic groups on this steps.
Can I ask you a question about the statement?
Yeah.
So Fark Fontaine X diamond is much larger than X diamond, right? So is this not some sort of like right? Maybe you'll explain.
I will explain how you construct this. So we give a sketch of proof, and I will make the assumption that, but actually that's maybe a question for the audience. I don't know how restrictive it is. I want to assume that G is an open subgroup inside the QP points of a reductive, or maybe just some algebraic group over QP. I just realized before the talk that I'm not sure how restrictive an assumption it is on the p-adic Lie group, like whether I can always realize a p-adic Lie group as open inside. Well, maybe just some open in my p-adic Lie group can be.
I think a bit like some open should have a faithful. I think it should have a faithful representation, and then it should be. Then it's closed inside. If it's compact, it has a faithful representation, but then it's kind of closed inside the GLN, and then that you have over QP, you have this Catan theorem. The only closed subgroup is automatically self-analytic, which we knew anyway. But I think. I mean, it sounds closer to us having a faithful representation, which I think is just true.
Okay, so probably that's maybe. Okay, I wanted to assume that G is open in GQP, where G is an algebraic group. Over QP, so maybe that's. Can always be arranged, but let me just put this as an assumption. So assume this. Just in case. So then I want to make use of this. I can write this classifying stack of GLA as the classifying stack of G smooth times the classifying stack of the RAM stack of this rigid. So it's up here an algebraic group, but I see it as a Gelfand stack, so that's like taking some kind of analytification of G. I will still denote it like this, just by like just with the same letter. Right. So I have this formula describing GLA, which I explained in my first talk, describing the localytic incarnation of G as some kind of like overconversion neighborhood of G smooth inside the rigid analytic group G. And so for 1, and the argument will be the same for 2. For 1, now you see that you want to. So you have a functor like this, but in the other direction, how do you cook up a GLA torsor on the hot state stack if you have one on this uniform completion? Well, so you want to map the hot state stack to be GLA, so you have to map to this fiber product. But maybe the first observation here is that maps from, like for any, let's say any Gelfand stack or even arc stack over MRQP, we know that maps from X hot state to Y the RAM, because the RAM stack was defined as a right adjoint, so it's the same as taking the perfect utilization and mapping to Y. But this is just the same as the perfect utilization of X. Which I can in turn rewrite now using this. This I can rewrite as morphisms from which I can also rewrite as this way. Okay, so now I will apply this to Y, which is either BG, or let's say BGLA, for example, or BG. So it will be my rigid analytic. So in both cases, the de Rham stack is either BG smooth or BG. So we see that on these two pieces, like basically mapping from the Hochschild stack or the uniform completion is just the same because these are the Rham stack, it's just the same as mapping from the perfect fluidization. And they both have the same perfect fluidization. So now we have to deal with this other factor. Now, using the Tanakian description of G torsors, we see that basically it really reduces to a claim on vector bundles. And so for this other factor, in fact, we know that G torsors for this algebraic group G are the same for X Hochschild and uniform completion of X diamond because of what we proved in the first, my very first theorem, that vector bundles on the two stacks are the same. First theorem implies that maps so now you put everything together and you deduce this natural functor, pullback functor is on. But then this last bit is really just this adjunction between this hard functor and uniform completion and the perfect realization. So recall that this hard functor was defined as a left adjoint to perfect realization. The exact same argument as proof of this first equivalence would just apply as well in this case, because I just used some claim on the Rham stacks in the first part, and then I use this decompletion like this. My first theorem, which is valid on the Hochschild locus, but also on the whole twistor stack. So same argument for 2, basically. And now for 3, so how you want to produce, you start with a perfect, like just a G torsor on the pro-étal sense on the diamond, and you want to produce a GLA torsor on the relative curve. So again, you have this fiber product formula. Well, for mapping to BG smooth or BG de Rham, it's again just a statement which you can read on the de Rham stack. So it's just something that depends on the underlying, on the perfect fluidization on this relative Falk-Fontaine curve, so that you get just from this information. So the tricky part is just to get a map from the relative Falk-Fontaine curve to BG. And for that, so the observation is for 3. I will use the result of Kedlaya and Liu, which tell you that maps from X diamond to the QP points of G. This has a natural map, which is even fully faithful to maps from the relative Falk-Fontaine curve to and so in particular, G is so composite. Here. I get by composition. So here, let's say G is GLN for simplicity. I'm saying that the statement is saying that rank n pro-étal QP local systems on X give rise to G bundles so to rank a vector bundle on the relative Fark-Fontaine curve. In fact, they even show that this is the image of this functor is an equivalence with the category of semi-stable slope 0 rank n vector bundle. So you can describe the image. Okay, so that's, I think, basically the argument for this. So it's just in some sense like combining some information on the RAM stacks with this this kind of p-adic non-abelian Hodge theory statement for vector bundles that we made. So of course, then a question you can ask is, and that's some of the second part of the result, that we stated as a proposition. What is concretely this torsor? So let's same setup, but so let me write. So X is again as before, and let's say I have a point like a G torsor on X diamond, where this one is a perfect Lie space. Then last part of my theorem tell me that this X tilde should give rise to this perfect Lie space. X tilde should give rise to a certain GLA torsor on the p-adic twistor stack. And the proposition is basically that if Fark-Fontaine X tilde is classically decompleted in the sense of definition before, then for the G action, so this action of G, then the GLA torsor on X div 1 corresponding to X tilde by my previous corollary is simply given by these locally analytic vectors in Fark-Fontaine of X tilde. And maybe I put it here, plus same statement on the Hodge state locus using not the relative Fark-Fontaine curve, but just the locally analytic vectors inside X tilde. Okay, so the logic here is we started from this explicit description of the div 1, the twistor stack or the Hodge state stack in terms of local analytic vectors when X is GM using a particular perfect Lie cover, like this kind of toric chart or cyclotonic cover. Using this, we were able to prove this kind of general like this non-abelian Hodge theory statement. But then in turn, we can use it to deduce that if we now pick another perfect Lie cover under this assumption, then in fact this torsor is of this form. In other words, i.e. the twistor stack is just the quotient of these local analytic vectors GLA. So that gives me other possible presentations of my twistor stack or of the Hodge state stack. Of course, for this to hold, you have to ensure that this is these spaces are classically decompleted. And I don't really know a good criterion which ensures this on the Fark-Fontaine curve. But at least on the Hodge state locus, there are such statements. Like if you, I will come back to this. So Lurie has discussed this geometric morphism, and when one knows that it is surjective, then one also knows that these higher derived local analytic vectors vanish. That was basically what we explained in the case of the modular curve last week. So in some situations you can show such a thing. Maybe because I mentioned Lure's talk, let me remark that we somehow saw that, like, so recall first of all that in general X Hodge state. So maybe I will work relative to CP for simplicity. So X is now So in everything I said, X was always assumed to be smooth over QP. Let me know to make things a bit simpler. Let me switch to the geometric setting. So X is no smooth rigid space over CP. I recall that we have this natural map from X such state. Well, actually, sorry. In fact, relative or not does not matter at the level of the Hodge state stack. I have this map, and it is a germ bounded by the tangent bundle over convergent. That was part of this general description of the geometry of the Hodge state locus. But this is something we saw somehow in Lure's talk. So let's take X to be the modular curve. And then, okay, the fact that the Hodge state stack is a germ over X, it means that when I form the fiber product of the Hodge state stack with itself, I should just get the Hodge state stack times the classifying stack of this tangent bundle. Right? But now let me combine this with this proposition. So this proposition tells me that, plus some implicit vanishing of higher derived local analytic vectors, tell me that I can write X such state as, so maybe my X was a modular curve at finite level, so K away from P, KP, so. And let's take X tilde to be X infinite level at P. And G is, so that's a torsor over XK for KP. Right, and so now, so what do you get when you, so let me replace in this formula the Hodge state stack. So I know by the previous proposition that the Hodge state stack of my finite level modular curve is just X tilde LA, so it's perfectoid modular curve. Take local analytic vectors, and then I mod out by KPLA. Okay, so if I replace X Hodge state in this formula by this explicit quotient of a Berkovich space by a local analytic p-adic Lie group, and I take the corresponding KPLA times KPLA torsor over it, that gives me the formula that X perfectoid modular curve, locally analytic vectors times fiber product with itself over the finite level modular curve. Well, this will be something like XKPLA times GLA times KPLA, and then I have to mod out by this over convergent. Right, so if you write concretely, let me put it here. If you write this concretely in terms of functions, that tells you that basically, like when you look at this sheaf of local analytic vectors, and you tensor it with itself over the finite level modular curve, that's something like locally analytic functions on KP valued in this sheaf of logarithmic functions, and then you need to take, get some invariance by, so the tangent bundle, in this case, you describe Kodera-Spencer as just this N0. So this kind of formula that Lurie was writing, it's basically, if you want, one way to think of it in terms of the Hodge state stack is just a combination of the fact that this is a germ for the overconvergent tangent bundle, together with the claim that it is explicitly presented as this quotient of logarithmic vectors by KP action. Right, so it's important to note that this locally, this is KP torsor, if you want to say for
something like a GL2Z p tensor. But when I pass to local analytic vectors, it's not anymore a GL2Z p tensor over X, but it is a GL2Z p LA tensor over the Roche stack, which is a germ over X. So that's why somehow, if it was literally a KP tensor over X, you would get a formula like this, right? And this is that you have to add something here. It's related to the fact that it's rather a tensor over the Roche stack, which is a germ. So that's one way to think about these formulas. And let me maybe continue along these lines to also explain how to think about maybe other statements that Lurie has explained. So for this, I will just, again, just focus on what happened on the Roche state locus. So recall some statements that Lurie mentioned in this lecture. So one of them was that if you have a proétal, let's say equal to W, is a proétal vector bundle. So X is as before, a smooth rigid space over CP. Note that from the perspective of this lecture, this is really just vector bundle on X. Another way of writing this category. He made this claim that this comes equipped with a canonical X field from W to W tensor omega 1 X over CP with a tail twist. And he also explains the following result, that if you have a G tensor where G is a p-adic group as before, then there exists a certain morphism which is called the geometric cell morphism, which goes from Lie G dual tensor O hat to omega 1 of X over CP tensor O hat minus 1 with the property that such that if V is a locally analytic G representation with QP coefficients, then I can look at the following. So I can take the corresponding V gives rise to proétal and W. So V gives rise to a proétal vector bundle just by base change from QP to the structure, completed structure shift. And the claim was that this geometric cell morphism has the property that this cell operator that I have, it will factor. So I have that W. So I will produce a certain factorization of this Higgs field, or cell operator as you like, on W. And how do I do that? Well, I first, so by definition, this is V tensor O hat. And because V has a local analytic G action, I can differentiate the G action. So that gives me give me a map from Lie G times V to V, but I can put this on the other side, and I get a map from V to V tensor the dual of the Lie algebra. And then I can tensor over QP with O hat. Okay, so here I can just, so that's my derivation of the G action. I denote it like that, tensor the identity on O hat. And here this is my geometric, if you write this as V tensor O hat, tensor omega 1. And then this map is just the identity on V times the geometric cell morphism. Yeah, so that's the property of this. So how to think, now I want to explain how you can think of these two statements in terms of
Sorry, can I? So what is the definition of W? W is V tensor QP with O hat X? Sorry, are you using the G action there to descend?
Yeah, correct, yes. Maybe that's not very good notation. I just want to consider the proetal Hat module, which is given on X tilde is given by this representation with its G action, and I use this G action to descend it to proetal module on X itself. Right. Okay. So how to think about this statement? Well, so interpretation by X such state. Well, for the first one, by my main theorem, a vector bundle on X, a proetal vector bundle is the same as a vector bundle on the Hodge-State stack. But now the Hodge-State stack, as I recall, is a germ for like bounded by this over-convergent module. Right, so in particular, you have an action of this on the X Hodge state, such that the composition with the zero section here is just the identity. So this is just the identity. So whenever I have a vector bundle on the Hodge, or in fact any quasi-coherent chip on the Hodge state stack, then I can, if I pull back along this composition, it's just itself. So you see that it actually naturally arises from an object there, but this just this classifying stack of T dagger is Cartier dual to the analytic cotangent bundle with a twist -1. And so this means that an object here is just, if I further pull back to, here I can further pull back to this, again, this uniform completion. And so I just get an object here together with the Higgs field. That's why you get this canonical Higgs field. So you get a refined information. You get something already at the level of the Hodge state stack, but then you can further pull back to the, so to say, to the proetal site and get this part one. In fact, you get it whenever you have a complex of an object on the quasi-coherent chip here, which descends to the Hodge state stack. Under this kind of local analytic, this will also satisfy this property, and that was somehow implicit in like getting this Sen operator as well for such objects. Okay, so we expect to us that you don't have to start necessarily with a vector bundle, but can extend to more general quasi-coherent chips. Okay, and so what is this morphism 2 and this factorization? Well, the claim here is that, so for 2, the idea is that you can look, so there I will use my decompletion statement. So I have this proetal G also on X, and by what we said before, so X tilde gives rise to a GLA torsor on the Hodge state stack. So it gives rise to a map from X Hodge state to BGLA. And so now I can just look at the map. So I also have a map to, so we get, because X Hodge state is also living over X, I get a map to from X Hodge state to the classifying stack of GLA relative to X. But now I can just look at the induced map on cotangent complexes. So this is relative to X. And well, this one is, because X Hodge state again is a germ for the over-convergent tangent bundle. What you get here is just omega-1 of X over Cp, and you get a twist coming from this twist over there. So that's what this map is, and here it's just basically after some base change to X, it's just computing the cotangent complex of such a classifying stack. I'm sorry, because this is a gerb, there is also a twist by -1. But here as well, it's a classifying stack, so I get the Lie algebra, the dual of the Lie algebra with a shift. But then base change to, sorry, here I should, the map is really from this to the Hodge-Tail stack. So it's really base change from QP to the Hodge-Tail stack. And yeah, so then the claim is basically that this geometric set morphism is nothing but this map after pullback to the uniform convection. This recovers the star after some shift. This recovers this morphism theta after shifting and pulling back to along the map from the uniform completion to the Hodge-Tail stack. This recovers this geometric set morphism. Right. So actually you get something better. So as a remark here, note that if X is not a smooth rigid space over QP, and then you get more structure because know this Hodge-Tail stack, it's not a gerb anymore. So it's a gerb for the over-convergent tangent bundle, but relative to the Hodge-Tail stack of the base, which is itself non-trivial. QP Hodge-Tail. So this is now a gerb for the cotangent complex relative to X. But this itself, QP Hodge-Tail itself, is a gerb over QP, over SPA QP, for GM dagger. So now if you, instead of taking, in this arithmetic situation, the cotangent complex, you can, of X Hodge-Tail relative to X, it will be an extension of this cotangent complex relative to X times QP Hodge-Tail by like the base change of the cotangent complex of basically of QP Hodge-Tail over SPA QP. Just by this property of any composition gives rise to a distinguished fiber sequence for cotangent complexes, but no by the same. So it's a gerb, so again you get just omega 1 of X over QP with a tail twist and a shift. And for this one, well, you just compute that this is basically just a structure shift. So, sorry, I everywhere forget some base change to the Hodge-Tail stack. So here as well. Right, but again, when you pull back to X diamond hat, it's like replacing the structure shift on the Hodge-Tail stack by this completed structure shift. And so here again, after shifting and pulling back to X hat, and this recovers the Falting extension. So I think Bhatt's philosophy from the ACM paper is that you should, it's in the integral setting, but I think the remark would apply as well here. And that was, I think, also the inspiration for Falting's extension, is that you can imagine X Hodge-Tail as some kind of twisted form of the classifying stack of X over F1, whatever that means. So if it is a perfect ring, should be formally étal over F1. So that's just the same as. So in the perfect case, it's really just usual omega 1. But QP is supposed to be smooth of dimension 1 over F1, so that's why you get this extra contribution. Anyway, so you get this, and this means that, in fact, in this arithmetic situation, as expected, you get a bit better than just the Higgs field. You get the Higgs field, but also an arithmetic set operator. And you can combine the two into a map, not to W tensor with omega 1, but with W tensor with the Faltings extension. Right, okay, and then this second part is basically just a consequence of this cotangent complex interpretation. All right, so maybe just to conclude, on Monday I will give another talk where I will try somehow to explain how to use this perspective for in relation, in this example, more directly relevant to the p-adic Lagrange program, so for example, local or global Chinois varieties. But for today, let me maybe just conclude by also maybe stressing something that I think we did not stress too much, that one advantage of having define some cohomology theories for rigid analytic spaces in terms of analytic stacks is that on any analytic stacks you have a category of quasi-coherent sheaves and a six-functor formalism. So another consequence of my very first theorem of today is that, so maybe I just put it as a concluding remark, is that if, again, X is smooth partially proper over either over QP or over a perfect base, this equivalence of perfect complexes that I stated in particular includes a comparison of cohomology, and so in particular it tells you that the cohomology, the coherent cohomology of the p-adic cluster stack is nothing but the poetal, so it's the cohomology of the relative Frankfurter curve, but by some kind of Artin-Schreier, this is the same as just the poetal QP cohomology. So one advantage of thinking of poetal QP cohomology as coherent cohomology on this stack is first of all that some structures on poetal cohomology you can interpret via the geometry of the stack. So this kind of, that was very apparent in Maximilian's lectures, using like relating, I don't know, poetal cohomology to syntomic cohomology or Yudokato cohomology via some geometric properties of all these various stacks. But you can also use that to understand like finiteness or Poincaré duality for this cohomology. Right? And so that's, I think, especially interesting in this situation because this poetal QP cohomology like behaves outside, say, the proper smooth case, it behaves a bit counterintuitively compared to other cohomology theories. So formulating finiteness or Poincaré duality in this context is not so easy, and this is possible using the p-adic cluster stack. And for basically for that you just need to see that if you have so that's a theorem that Max used and stated and used, that if you have a smooth morphism of rigid spaces, it gives rise to cohomologically smooth maps at the level of the div1 stack, and you can identify the dualizing sheaf. So once you have such statements, this gives you, like for free, some Poincaré duality results. Okay, I think that's all for today.
Questions? Can I ask just a general question? So I guess in all of these lectures we've been using Berkovich spaces, or some theory that's closer to Berkovich spaces, and so something like the usual unit disk is not really an object in that category, right?
Right.
And I was wondering, is there an analog of everything if you were to work with p-adic spaces?
Possibly, but I think it would require much more work because, for example, regarding this last point, I also have a paper with Hannes Anschütz and Lucas Mann, where instead of interpreting p-adic QP cohomology in terms of coherent cohomology of the twistor stack, we do that in terms of like maybe closer to just using relative arc-Fontaine curves. And in this, there we work really with V stacks. And then you have to, I think, work much harder to prove some nice descent properties, because you always work with like solid analytic ring structures. And so then proving like some basically that some morphisms are Schritt covers. I mean, we don't quite use theory of analytic stacks, but like proving that something is a Schritt cover when the analytic ring structures are not induced is much more work than in the induced case. It's really just proving that some morphism is descendable. So yeah, I think that would be it's more complicated. I guess in practice, most of the examples that seem relevant to for example, to the p-adic Langlands program, or to the geometrization of p-adic Langlands, or maybe typically in the work of Colmez Niziol or Colmez Gilles Niziol, when they study this Poincare duality statement, they often consider the partially proper case as well. So, in practice, it does not seem to be a big, like, too restrictive.
I got one small question. I was wondering, so what you explained in the first half of the lecture, you were explaining it over QP, but you're saying it's very general. Would it also work for these locally analytic representations more generally?
Yeah, I think this decompletion argument is really soft and very general. So it has to be checked, but I think it would work also in mixed characteristic basic. I don't see really a point for that to be So, of course, in this integral setting, it's also harder to set the twistor stack of the perfect prismatization of even for QP or for GM as the expected shape that relies on statistical computations that Maximilian did with integral coefficients, but yeah, that's something you also know. So I think it should apply as well. This type of problems.
Okay, so I guess